Our second lecture on stars will deal with how stars form, how they spend most of their lives, and their aging and final stages of life. The first thing we're going to use as a tool to help us understand the life of stars is something called the HR diagram. HR stands for Hertzsprung-Russell, which are the two people who devised this diagram. But before we talk about the specifics of it, let's review that when we were talking before about a star's temperature, and we talked about how that related to its luminosity, and we also talked about how that related to its color, which we'll get to in a moment. But specifically, if we want to take a diagram and plot how bright a star is compared to how hot it is, then we might come up with something like an HR diagram, although it's a little bit what we would normally call the x-axis or the horizontal axis, maybe a little backwards from what you would expect. The vertical axis or the y-axis does increase in luminosity the higher up you go on the chart. So the higher up the x's on the right here appear, that represents brighter, I should say more luminous stars. Brighter again has to do with their distance and their luminosity. So how much energy they actually give off, how much light they actually give off, that's their luminosity. And the higher up you go on this diagram, the more luminous of a star you're dealing with. Temperature, like I said, is a little bit backwards of what you might expect. Hotter temperatures actually correspond to x's that are closer to the right-hand side of the diagram rather than the left-hand side of the diagram. So increasing temperature goes from right to left rather than left to right. But once we have we've plotted both the stars' temperature and brightness in this way, I'm sorry, temperature and luminosity. I apologize that I keep saying that. I don't want to confuse the idea of luminosity and brightness, because luminosity is inherent light that the star gives off, and brightness has to do with how far away we are. So I'm going to endeavor to be careful and say luminous. Once we have plotted how luminous a star is and how hot it is, we can do this by using the Stefan-Boltzmann law. And we basically come up with an XY coordinate that tells us where to indicate the position of the star's temperature and luminosity on the Hertzsprung-Russell diagram. And if we do this for a large number of stars, we notice a pattern start to unfold. Most of the stars exist for most of their lives on a swath that kind of goes diagonal from the upper left-hand part of the diagram towards the bottom lower right-hand part of the diagram. There's a little curve in there as well, but it's kind of just a diagonal line with a slight curve, and that is where most of the stars that we observe actually live most of their lives. So that consists of most of the stars. That particular region, or that swath, curved slanty region that most of the stars live on, is something that we call the main sequence. And so it just is empirically this region of the Hertzsprung-Russell diagram where you see the most stars. There are other places that stars exist. For example, you see a patch towards the bottom left-hand side of the Hertzsprung-Russell diagram. Those represent objects that are very hot in temperature, but they're not very luminous. So why would they not be luminous? Well, it has to do with the fact that they are very, very small. And the larger star you are, the more luminous, the more light you can give off. But if you're smaller, you can't give off as much light. So those objects in that bottom left-hand region are small objects, but they are actually very hot in temperature. Those are called white dwarf stars, which is a form of a stellar corpse that we will talk about in the next lecture. But they are stars that have already lived out their lives, and this is basically their skeleton left behind. There's also a region in the upper right-hand part of the Hertzsprung-Russell diagram where you see a good number of stars as well, maybe not as many as on the main sequence, but there exists a good number in the upper right-hand region of this diagram. These represent very luminous objects, but their surface temperatures are not very hot. So why might that be? Well, because they're kind of the opposite of the dwarf stars. They're very large, so they can give off a lot of light. It's just that the light that they're giving off is not very hot light. So those are where the giant stars are. And those are stars which are in their death throes. They will soon be cease to be stars any longer in the truest sense of the word, as in stars that have nuclear reactions occurring in their core. So they are the final stages of life exist. They're the geriatric stars there on the upper right-hand side of the diagram. Okay, so this particular Hertzsprung-Russell diagram labels all of these things and also gives you some examples of stars that you may or may not have heard of and what population they belong to. The Sun is on the main sequence because it's a middle-aged star about halfway through its lifetime. It's in the prime of its life, just existing on the main sequence along with most of the other stars. So Proxima Centauri, which is the closest star to us, is also on the main sequence, but you see it there very, very low on the lower right-hand side of the diagram. So that's telling you that this is a star that isn't very luminous. It appears bright to us because it's the closest star to us, but it's not very luminous, not outputting much light, and it's not very hot either because it's in the right-hand side near 3000 Kelvin. Some other stars that are a little bit more luminous than the Sun include Altair, Vega, Spica. You can see those depicted all along the main sequence. Gliese 876 is also marked here as being slightly dimmer than the Sun, and that is a star that's known to have an extrasolar planet. One of the smallest discovered when it was discovered was Gliese 876d. Some other stars that you may have heard of, Sirius B is actually a stellar corpse down in the white dwarf region. And then there's these older, aging stars in the upper right-hand part of the diagram that you've probably also heard of. Arcturus, Betelgeuse, Antares, Aldebaran, Rigel, all of those exist in the giant category, either red or blue giant stars. So incidentally, which one is hotter? Well, the bluer ones are going to be the hotter ones, as we know from Wien's law. So the blue giants are older stars that came from the main sequence as a hotter star to begin with, or a more luminous star to begin with. So Rigel, for example, is a hotter star than is Arcturus. Excuse me. The lines you see superimposed here on the Hertzsprung-Russell diagram indicate lines of the same radius. So any star that falls, for example, on the first line on the bottom left would only be 1/1000th of the radius of the Sun. Then the next line, if you're working from the bottom left towards the upper right, the next line you encounter says that all those stars, pretty much all those stars in the white dwarf region, are all about 1/100th of the radius of the Sun. That subscript that looks like a circle with a dot inside is the shorthand that we use to indicate Sun. So 1/100th of the radius of the Sun is approximately how big these white dwarf stars are. The next line up and to the right would be 1/10th of the Sun's radius, and that, you see, Barnard's star is roughly about 1/10 the size of the Sun. Then the next line up is indicates all stars that are basically about the same radius of the sun. And you see the sun exists logically on that line, and Alpha Centauri A and B are pretty close to about the same radius as the sun. Going up further, we have stars that are 10 times the radius of the sun, and those include roughly Spica, Capella. Those are all on the line that indicates the star is about 10 times the radius of the sun. Going even larger, you see objects, stars that are about 100 times the radius of the sun. So Rigel, Deneb, those stars are right on that line as being 100 times the size of the sun, which is pretty amazing when you think about it. But even those objects are not as large as the final line in the upper right-hand corner, that are objects that are 1,000 times the radius of the sun. So Betelgeuse, for example, is right on that line, 1,000 times larger than the radius of the sun. So if we were to empirically show how mass is related to luminosity, there is a relation here that luminosity is equal to about mass times to the 3.5 power. So not exactly mass cubed, but not exactly mass to the 4th power. It roughly falls along a plot that would indicate mass times 3 to the mass to the 3.5 power. So basically, the more massive you are, the more luminous you are. And that sort of makes sense when we were talking about the size of the stars, and they can give off more light that way. So as you're working your way up from the bottom right to the upper left of the main sequence, you're getting more and more massive stars, in addition to more and more luminous and more hot stars. You also see the spectral classes superimposed here on the top of the Hertzsprung-Russell diagram. So if you draw your finger down from spectral class G, you see that the sun is right there in spectral class G, and that the hottest, most luminous stars are in spectral class O, and the coolest, dimmest stars there are in spectral class M. So from this we take that more massive stars burn brighter. The more mass you have, and that makes sense, the more mass you have, the more fuel you have to exhaust and turn into luminous energy. So just like we had spectral classes, we have something called luminosity classes, which are just regions of the Hertzsprung-Russell diagram that are given labels. So for example, luminosity class 5 are the stars that exist on the main sequence. And then we have some subgiant categories, giant categories, and supergiant categories as well. So here they are all in one chart for you to keep track of all of these things. But the brightest, the supergiants like Rigel and Betelgeuse, those are both, by the way, in the constellation of Orion, are luminosity class 1A. Supergiants are luminosity class 1B. And there's some examples of each of these as you go down. So as you're going down on this chart, you're getting cooler and smaller stars that you're dealing with until you get to the main sequence here at the bottom, luminosity class 5. You may wonder, well, where is the white dwarf class? Well, this is really, this chart consists of luminosity classes of stars in the sense that they are still burning fuel in their core. As I mentioned earlier, white dwarfs are like stellar corpses. There's no fusion reactions taking place anymore, so they're not really a star in the truest sense of the word. They're just the skeleton left behind. And so speaking of how do we get to these stellar corpses, what happens as a star ages? We'll talk more about the actual death of stars in the next lecture and the corpses that they leave behind, but we can talk about how a star forms and how it ages up until the point where it meets its demise. But basically, we are able to, by looking at stars in different stages of life, figure out, and also based on atomic science, figure out kind of how they proceed through their lifespan when they start to exhaust the fuel that they have to burn at their core. So what is happening with a star during most of its life is that it's in a state of rough equilibrium, so that the pressure that would want to blow the star out due to all of this energy that is outputting is almost exactly balanced by the inward pull of gravity that wants to attract all this mass to each other into a single point. So gravity is trying to pull in, pressure is trying to push out, and when that's in balance, then that's when the star is in rough equilibrium, which is how the star exists for most of its life. But eventually that balance is tipped because the star starts to run out of fuel at its core in order to create that pressure against gravity. So what happens then? So in a nutshell, this is basically the life of a star like our sun. It starts out in the upper left as a huge cloud of gas and dust, many light years across. And then through random motion that becomes maybe perturbed by a passing nearby star, other gravitational interference, it starts to go in a circular motion and form a circumstellar disk. And at the center of that disk you have a star that's forming, and perhaps any planets that are going to form out of the disk surrounding the star of gas and dust. This process is kind of messy, and so the star spews out these flows from its poles as this is happening, but eventually the dust settles, literally, and you end up with a star, perhaps like our sun, and maybe orbiting the star are a number of planets that are much smaller than the star. The star will exist like our sun is roughly for billions of years, about 10 billion years for a star like our sun. We're about halfway through that lifespan right now at about 4.5 billion years. And so eventually when that 10 billion years runs up, it will start to run out of fuel in its core. And during this loss of stuff to burn, the star will go through a series of stages where it increases in its radius, becoming very bloated and turning into a red giant star. Then it will start to burn a different fuel in its core, which will be helium. And so it goes back into a yellow color. And then when helium runs out, these successive stages are shorter and shorter in the lifespan. Then it becomes an even larger giant star, and to the point where it doesn't have anything left to burn at all. It will shed its outer layers. It does not explode in a supernova. The sun will never, ever, ever turn into a black hole or supernova. That only happens with the most massive stars, but that's a common misconception. So I wanted to address that. Instead, relatively gently by comparison, it will just shed its outer layers, and what's left behind is kind of like its skeleton or corpse, which is the central white dwarf star. So incidentally, when the sun bloats to become a red giant, having run out of hydrogen to fuse in its core, its radius will become about 30 times larger than what it is now, and possibly more. And so in these final stages, when it becomes bloated like this, the radius of the sun itself will extend beyond some of the inner planets and basically incinerate the terrestrial worlds. So any life that would exist on the Earth at that time would be completely obliterated from the heat and radiation of the sun incinerating it. Now, a more massive star that starts out being much, much larger than the sun itself will actually go through a different ending. The beginning part is very similar. You start with your cloud of gas, it rotates, you end up with your protostar, and eventually your star. This star, though, is burning a lot faster through its fuel. So, ironically, even though it has so much more mass, it's going to go through it way, way faster. And so, instead of exhausting its fuel in billions of years, it will instead only be millions of years, and eventually it will also run out of fuel. It will try and fuse other elements, and it can actually, because of the intense gravitational pressure at its core, it can fuse elements heavier than helium. The sun, we said after helium, that's it. It can't really fuse anything else. More massive stars are able to fuse heavier elements, but eventually when they reach iron, that's the end of the road. They cannot fuse anything fruitfully after that to gain energy, so they run out of fuel entirely and they explode quite violently in a supernova explosion. And what's left behind in the center is either a neutron star or a black hole, depending on the mass of the star to begin with. You need a very massive star to start with, and the really, really, really massive ones will end up with a black hole at the center, but most of them will end up with a neutron star. So if you want to track how the star lives its life, you can follow the arrows depicted here on the Hertzsprung-Russell diagram. A star like our sun will start out on the right-hand side just as a cold, cold cloud that doesn't even show up. But eventually it begins to, its temperature rises, it begins to glow, and then it follows this track onto the main sequence. Then it goes through those series where it tries to burn other things at the end of its life in the red giant and yellow giant phases, and then once it ejects its outer layers and sheds its outer layers, it quickly goes from that red giant region all the way down to the white dwarf that is left behind. The blue track here with the arrows indicates the life of a more massive star. So you see it starts out brighter to begin with, and when it reaches the main sequence, it lives there for a while, and then evolves off of the main sequence into the giant phase, and then ultimately explodes as a supernova. So let's look at the birth of stars to start with. We've talked about this a number of times, but let's look at it a little bit more in detail. You have your interstellar cloud of gas and dust that's sort of going in random motion. Over millions of years, perhaps something happens to perturb this gas, and instead of becoming a cloud, then it takes on a more uniform motion where it's moving in a circular pattern. It's still very large in extent right now, about half a light year across. But as it starts rotating, the faster it moves and the faster it spins. Conservation of angular momentum requires that the size of it shrinks as it starts spinning faster and faster. And so eventually you end up with something just a few hundred AU across with a protostar, most of the mass concentrated in the center, that is going to start to burn in its core nuclear reactions. And as I said, during this process there's sort of overflow, spillage that flows out in the polar regions of the star. It's gaining so much mass so fast that it can't incorporate it all at once, and so some of it outflows in the polar region. The leftover gas and dust are what the planets form out of. So these molecular clouds are out there in space. We have seen them, and some of them are very large, and some of them are even larger. The larger the cloud to start with, the larger a star you can get out of it. So here are some examples of protostars that are enshrouded still in the gas and dust, that so that you can't actually really see them unless you look in the infrared, but their gas and dust is still there surrounding them. These are baby stars about to be born. And so here are some of those infrared images. If we look in those wavelengths, we can kind of see through the dust and gas a little bit and inside to see that there is a central star, and there are various sizes depending on which one we look at. In the middle, that protostar is starting to shine. Here's an image that shows you a little bit what these bipolar flows look like, these jets that are ejecting material in the polar regions of the star as it's forming. And so here is another set of tracks, but this is only the birth of stars instead of their entire lifespan. So this is how stars would begin their lives until they reach the main sequence, and the various tracks you see depict how much mass there is to start with, and how much mass there is to start with will decide where on the Hertzsprung-Russell diagram they end up for the zero-age main sequence. So once they reach the main sequence, we call that zero-age main sequence. They are now a star in the full sense of the word, where they're burning, they're having fusion reactions in their core, and they're in a state of relative equilibrium where they will spend most of their lives. That point in time, when they reach the main sequence, zero-age main sequence, we like to abbreviate that as astronomers as ZAMS, Z-A-M-S, zero-age main sequence. So how big of a star can you have, and how small of a star can you have? Well, if you have a star that is too small, then you do not have enough density in the core and compression in the core to ever sustain fusion reactions. So anything below about 10% of the mass of the sun, you're not really dealing with a star, you're dealing with something called a brown dwarf. A brown dwarf isn't really a planet, it isn't really a star. It can have bouts of fusion reactions taking place, but they can't be sustained because it's just simply not massive enough. So they glow in an infrared kind of way, but they do not shine like a star would shine. They do have some of their own luminous output, unlike planets for the most part, which don't, but it's not the kind of luminous output that you would have if true fusion reactions were taking place in the core in a sustained way. And above, on the other end of the spectrum, above about 150 times the mass of the sun, then you can't even really pull things together without them just blowing apart. So that is probably the theoretical upper limit to how large of a star you could possibly have. So again, here are some tracks of the birth of various stars. This is very similar to the Hertzsprung-Russell diagram that we saw earlier. And so let's talk about how stars spend most of their lives on the main sequence. When you have very low mass stars, it takes them a while to actually get compressed enough to the point that they reach ZAMS, they reach zero-age main sequence, and are in that state of relative equilibrium. Higher mass stars go through all of their stages very quickly, including their birth. Just because they have that stronger gravitational force due to the fact of how much mass is present, and all that mass attracting each other gravitationally. So again, this is the same sort of flow chart we talked about earlier, about that balance between the hydrostatic equilibrium balance between gravity tending to pull in and pressure tending to blow out. And the pressure then is created from the heat of these fusion reactions. But eventually this balance will become tipped where the fusion reactions can no longer be sustained. For now, though, low mass stars pretty much go through fusion reactions in the proton-proton cycle, where they're fusing hydrogen atoms, or hydrogen ions, I guess I should say, together. Higher mass stars go through a little bit more complicated nuclear reactions, which involve carbon and nitrogen, and so that's called the CNO cycle. It's really not important that you know the details of this, but the image to the left shows you how these different elements fuse together, carbon and nitrogen and oxygen. So you may remember from science classes that you've taken in the past that heat can transfer in different ways. There can be convection, conduction, and radiation. Convection occurs in pretty much all stars, but where it occurs in the star depends a little bit on the size of the star. So when you have these smaller stars that are about a tenth the size of the sun, then you have convection throughout. Whereas a star the size of the sun, you only have convection taking place in the uppermost layers, and then the very high mass stars have convection taking place deeper within towards the core of the star. So this kind of summarizes some of the things that I've already touched on, and that's that the stars will spend most of their lives on the main sequence. Eventually they will run out of fuel, and the higher mass the star is to begin with, the faster it will burn through that fuel. Okay, so this main sequence does have some width to it. The zero-age main sequence is a little bit lower and to the left of where you are when you're about to leave the main sequence, which is more towards the upper right end of the swath. So let's look at some of the giant stars. After you're about to evolve off the main sequence, then you end up in the giant region. So why that happens is because basically you run out of hydrogen in your core. You've fused it and fused it and fused it into helium, and now there are no more hydrogen, or very few hydrogen ions left for you to fuse. So once that happens, your core consists mostly of helium. And so having no real fusion reactions taking place anymore, gravity starts to put a chokehold on things and the core contracts. And when this happens, though, then the core is able to heat up. And because of that heating up, then suddenly a shell around the core begins fusing hydrogen, and this causes a burst of energy. I wouldn't say a burst because it's not actually fast in terms of what we're thinking of, but it is fast in terms of the lifetime of the star, and so then this causes the star to expand now in its outer layers. Eventually, the core becomes so hot from this contraction that helium can fuse in its core. Instead of now burning hydrogen, the core starts burning helium. And the hydrogen shell reactions are still taking place, and this produces so much energy that the star expands even further into the giant stage. And this is basically the beginning of the end for the star. So here are the tracks that represent the end of the life of the stars. So they're going to evolve off of the main sequence and over towards the upper right-hand region where the giant stars exist. And they take different tracks to get there depending on how massive the star is to start with. So once you have that high temperature at the core where helium can fuse, now helium will fuse into beryllium, and that will fuse into with helium into carbon. But that requires the temperature to be about 10 times as great as it is when you just have hydrogen. So that can only take place once that core starts to contract and the temperatures become very, very high. So this gives the star a new source of energy, but there's less of it than there was of the hydrogen. So it's not going to be able to sustain these kind of reactions, and the reactions are taking place at a hotter temperature, so it's going to burn through these reactions quickly, and so it's going to exhaust its helium source of fuel much, much, much faster than it will exhaust its hydrogen source of fuel. And so the further tracks you see here on the red represent when it starts fusing helium in the core, and eventually it will run out of that as well. And we'll talk about what happens in the actual death of the star again next time. But because the star is sort of unstable now in its fuel source, think of it as resources are tight, it has to scrimp, and sometimes it's able to make do and other times not, and so its brightness will change over time. Here's a set of two images of the same star, and you see in one set that it's much dimmer than in the other set. This is a variable star, is what we call this, where it's changing in brightness. Its brightness varies over time. And some of these stars vary in a regular, predictable way. The Cepheid variable, for example, occurs in a way that's easily predictable, and we can actually use those to tell how luminous the star is based on its period. I'm sorry, how far away the star is based on its period, because its luminosity being known. So what I mean by that is that the faster a Cepheid, Cepheid's period of variability, the less luminous it is. So if it takes about 100 days to go through its period of brightness change, then we know something about its luminosity as being greater than 10 to the 4 times that of the sun. And so since it falls in this predictable way, we can use it as a standard candle, because if we know that if we just time the variability, then we can say, oh, well, this must be a star which is 1,000 times the luminosity of the sun, for example. And then if it looks to us like much, much dimmer than that, then we can deduce exactly how far that Cepheid variable is. And so we use this as what we call a standard candle. It's one of the kind of stars that we know a priori what its luminosity ought to be, and based on how bright it appears, then we can deduce how far away it is. So Cepheids are interesting for that reason, but there are other variable stars that are depicted here on the HR diagram. And so anything in this strip is unstable, this instability strip. This is something that is teetering on the edge of existence.